Welcome to this third lecture on the topic of milliequivalents, millimoles, and milliosmoles. And this is my favorite lecture of the three because I don't have to say anything new. We've already covered all of these topics. So our only objective here is for you to complete a bunch of practice problems so you can demonstrate your mastery of this subject. So with that as enough of an introduction, let's go ahead and get started. The first problem reads, a physician orders magnesium sulfate to be administered at a rate of 50 milliliters per hour to a patient experiencing premature labor. The pharmacy sends up 50 milliliters of a 4% solution. And it says to note that magnesium sulfate heptahydrate, which is the form of the magnesium sulfate in the solution, has the formula MgSO4 with 7 water molecules and has a molecular weight of 246. So given that situation, and again, it is common to use magnesium sulfate in the labor and delivery unit when they want to stop or kind of slow down a premature labor. So it works as kind of a muscle relaxant to try to avoid the contractions. So with that said, we've sent up this 50 milliliters of a 4% solution. The first question asks, how many milliequivalents per hour of magnesium will this patient receive? Okay. So with all of these questions, it's always kind of confusing on where to start. Well, they'll start with the fact that they're going to be receiving this magnesium sulfate at a particular rate. They are receiving 50 milliliters per hour. So essentially what we want to know is instead of a volume per time, we want to know how many milliequivalents per time. So everything still will be expressed per hour. So let's start with the fact that they told us we were going to administer 50 milliliters of this solution per hour. So we'll start with that, and then we'll carefully cross our units and go from milliliters and end up with milliequivalents. So our first conversion is to multiply the 50 milliliters per hour times the concentration of the magnesium sulfate in the solution, expressed as 4 grams of magnesium sulfate per 100 milliliters. And this is an important concentration to be able to extract from the question that said that we had a 4% solution. The 4% implies a weight per volume concentration, and 4% therefore would mean 4 grams for every 100 milliliters. That's what a percent is. It's per 100. So that's where we got our conversion and basically where we can set up 4 grams of magnesium sulfate over 100 mils. So when we multiply that, the units of milliliters cancel, and we're in grams of magnesium sulfate. Our next step is to convert grams to milligrams by simply multiplying by 1,000 milligrams over every 1 gram, so that grams cancel. We're now in milligrams of magnesium sulfate. And there now is where we need to convert from our weight to the number of molecules. So we'll multiply that by the fact that we know that for every 1 millimole of magnesium sulfate, there would be 246 milligrams of magnesium sulfate, since 246 is the molecular weight for the magnesium sulfate heptahydrate. Okay, so that will cancel our milligram units, and now we're in the number of molecules of magnesium sulfate. However, this question wants to know the number of milliequivalents of magnesium. So we need to convert from the parent molecule, magnesium sulfate, to just the number of magnesium molecules. So we'll multiply that by the fact that looking at the formula for magnesium sulfate, every 1 parent molecule only has 1 magnesium. There's 1 magnesium and 1 sulfate. Therefore, we can multiply with the fact that for every 1 millimole of magnesium ion, there is 1 millimole of magnesium sulfate, the parent molecule. Now, that converts us to just the number of molecules in this form of millimoles of the magnesium ion. Now we can finally convert to milliequivalents by multiplying it by the fact that since the valence of the magnesium ion is 2, it has a positive 2, then that valence number 2 will go with the milliequivalents, and so we have 2 milliequivalents of magnesium per every 1 millimole of magnesium. Millimoles of magnesium cancel, and we now have our final units being milliequivalents of magnesium. So if you do all that math, starting from the left, going to the right, the number you should get in the end is 16.26 milliequivalents of magnesium. And I'll remind you, all of that was still per hour. So that answers this question. The answer is 16.26 milliequivalents of magnesium per hour is the rate of magnesium this patient is receiving when they're infused this solution at 50 milliliters per hour. All right, part B says, okay, go further. What is the osmolarity of this solution in milliosmoles per liter? All right. So One thing that where we're going to start this question with is the fact that it wants to know the osmolarity, which is the milliosmoles per liter. So we're going to need to know our milliosmoles standardized for the volume of a liter. Okay, so let's start with 1 liter, and then we're going to determine how much magnesium sulfate is in there, convert it to the number of molecules, and then convert it to the number of milliosmoles, one step at a time. So starting on the far left with what we want is to determine this amount per liter. So let's start with 1,000 milliliters. We then multiply that by the concentration of the magnesium sulfate, which we said was 4 grams for every 100 milliliters. Milliliters cancel, and we're in grams of magnesium sulfate. Convert that to milligrams by multiplying by 1,000 milligrams of magnesium sulfate for every 1 gram of magnesium sulfate. Now we're in milligrams. Do the same conversion to molecules of magnesium sulfate by multiplying by the fact that 1 mole of magnesium sulfate would have 246 milligrams, since that's the formula weight. Milligrams cancel, and now we're in the number of molecules. So what's different now, be careful, we're not converting to milliequivalents, so we're not going to look at the valence of the molecule. But when the parent molecule does dissociate into solution, given the formula for magnesium sulfate, which is MgSO4, it would separate into 1 magnesium molecule and 1 sulfate molecule. Those are the only molecules that are going to produce any sort of osmotic force. So you essentially have 2 particles. Therefore, we're going to multiply by the fact that you would have 2 milliosmoles for every 1 millimole of magnesium sulfate. 1 molecule magnesium sulfate produces 2 particles, 1 magnesium, 1 sulfate. So there are 2 milliosmoles for every 1 millimole of magnesium sulfate. So once again, if you do that math all the way from left to right going across, you would see that the final numeric answer would be 325. And the units, I'll remind you, are in milliosmoles per liter, because this is the number that we calculated was based off of having 1,000 milliliters or 1 liter. So our answer is 325 milliosmoles per liter. Good. Which is kind of cool. Before we go on to the next question is to look up above, and I've included the actual package labeling from a vial of magnesium sulfate. And if you look in the little print down below there, it says that for each 50 milliliters of sterile solution contains magnesium sulfate heptahydrate, 2 grams, and in parentheses it says equivalent to 16.25 milliequivalents of magnesium. So, once again, that confirms our answer for letter A, since that's the number of milliequivalents per 50 milliliters, and that's what we calculated. And then going on further, it goes on and says make and contain, but the last sentence includes that it would have a osmolarity of 325 milliosmoles per liter. So we were able to essentially calculate the same information that's included on the package labeling. All right, let's start our next question, which is about calcium. And it reads, which contains the most milliequivalents of calcium? A calcium carbonate 600 milligram tablet or a calcium citrate 950 milligram tablet? All right, and some additional information for both is that calcium carbonate with the formula of CaCO3 has a molecular weight of 100, whereas the calcium citrate has a formula of 3 calciums for every 2 citrates, you can see in the formula, and a molecular weight of 498.5. Okay? And again, what we're trying to decide is basically convert the weight. We were given a weight of 1 tablet for both the calcium carbonate and the calcium citrate, and it's asking, well, how many milliequivalents of calcium does each of those 2 tablets provide? And then we can conclude which one has most. Well, let's just start with the calcium carbonate. So I'll start with the fact that we were told that each tablet weighs 600 milligrams. And so we have 600 milligrams of calcium carbonate. The first thing I want to do is convert that to the number of molecules of calcium carbonate by multiplying by the fact that 1 millimole of calcium carbonate would have 100 milligrams, because the formula weight is 100 milligrams. Therefore, milligrams of calcium carbonate cancel, and we're in the number of molecules or millimoles of calcium carbonate. But now the trick is we want to know the milliequivalents of calcium. So we have to look at the formula, and since it's 1 calcium for every 1 carbonate molecule, we can multiply this by the fact that there would be 1 millimole of calcium, the ion, for every 1 millimole of calcium carbonate, the parent molecule. That way the millimoles of calcium carbonate cancel, and we're in just millimoles of calcium. Now we can finally convert that over to the milliequivalents by looking at the valence. And since calcium has a valence of positive 2, then we would take the 2 number for the valence and put it with the milliequivalents. So there are 2 milliequivalents of calcium for every 1 millimole of calcium. Millimoles of calcium cancel, and our final units would be milliequivalents of calcium. And if you do the math from left to right, your numeric value should be 12. So essentially we say that one 600 milligram tablet of calcium carbonate contains 12 milliequivalents of calcium. Now, let's answer that same question, but for the calcium citrate. So here we see the calcium citrate. On the left, I have that each tablet weighs 950 milligrams for the calcium citrate. Let's multiply that and convert it to the number of molecules by multiplying by, on top, 1 millimole of calcium citrate has 498.5 milligrams, and that's the formula weight. So milligrams of calcium citrate cancel. We're now in the number of molecules. Now this is where it gets a little bit trickier because we have to look at the formula for the parent molecule of calcium citrate, and we see that there are 3 calciums that combine with 2 citrate molecules. Okay, calcium, since it's positive 2, and citrate, since it's minus 3, means that you have to have 3 calciums to bind up a total of 2 of the citrate molecules. Why is that important? Because now to convert from calcium citrate to just calcium, we're going to multiply the fact that there are 3 calcium molecules for every 1 molecule of calcium citrate. Now we've converted into just the number of millimoles of calcium. We'll convert it to milliequivalents the same way we did before by multiplying by the fact that the valence on calcium is 2. So there are 2 milliequivalents of calcium for every 1 millimole. Millimoles cancel. Our final units would be milliequivalents of calcium. You do the math from left to right and you can see that the final answer is 11.4. So, one 950 milligram tablet of calcium citrate provides 11.4 milliequivalents of calcium. So to the answer to the question about which one contains the most, clearly we'd have to go with calcium carbonate, but you can tell these formulations are designed to provide nearly the same amount of calcium. Okay, and so could you choose either? Absolutely. Some people feel that the calcium citrate is a little bit easier to digest and not quite so rough on the stomach as the calcium carbonate. So there may be some patient-specific factors on choosing one form of the calcium versus the other. But essentially, you can tell the reason there are different numbers or weights of calcium is that the calcium carbonate 600 provides about 12 milliequivalents of calcium, whereas that same amount of calcium, maybe a little bit less, 11.4, is what you get when you use a 950 milligram calcium citrate tablet. And that's the end of this question. All right, let's go on to the next question. And I really like this question. I try to model it off of something you could see in retail practice with a commercial product called Naci Delayed Release Oral Suspension. And this product comes as a packet, actually, not actually as the liquid. It comes as these enteric-coated granules that you then mix in water and drink, essentially. So they come in packets, and each packet contains, or is labeled to contain, 40 milligrams of Nexium, meaning esomeprazole. So the active ingredient esomeprazole has 40 milligrams in each packet. However, the chemical itself isn't just pure esomeprazole. It actually comes as esomeprazole magnesium trihydrate. And since that's the actual chemical that's in the packet, the packet themselves contain 44.5 milligrams of this esomeprazole magnesium trihydrate. And I'll abbreviate that as EMT in my questions down below. So each packet has 40 milligrams of esomeprazole, but actually that is contained in 44.5 milligrams of this EMT, esomeprazole magnesium trihydrate. Also, on the right-hand side, this is the chemical formula straight out of the package insert. And you really can't answer these questions if you really don't understand the relationship between the active moiety esomeprazole and the parent molecule esomeprazole magnesium trihydrate. And that's best illustrated in this chemical formula. And you can see the complicated molecule in the brackets. That's esomeprazole. Clearly the therapeutic agent. But esomeprazole, when it gets into solution, basically is an ion, and it dissociates, and it has a -1 charge. For whatever reason, and this I don't know, but it's best formulated, therefore, as a salt, and the salt then is combined with the magnesium. And since magnesium has a positive 2 valence and esomeprazole has a negative 1 valence, you can see there are actually 2 esomeprazole moieties combined with 1 magnesium. And you can see the 2 next to the right-hand bracket. So keep in mind, even though this is a big, long molecule, there are actually 2 of those that bond ionically with the magnesium and 3 water molecules. That's what's really in the packet. Okay? And keep in mind, the last point before we read the questions is that I did give you the molecular weight of the parent molecule, the esomeprazole magnesium trihydrate, as 767.2 as the molecular weight. Okay, now, with all that said, let's answer a question. It says, how many millimoles of esomeprazole are contained in one box that contains 30 packets? Okay, where do we start? Well, let's start with, we said one box has 30 packets. So what we want to know is how many molecules in the form of millimoles of just esomeprazole are present in these 30 packets. So let's start with 30 packets and multiply by the weight of the esomeprazole magnesium trihydrate in each packet, which was 44.5. Okay, so, and that was the amount per packet. So the units of packets cancel, and now when we multiply that, 30 times the 44.5, that would tell us the total weight in milligrams of the EMT. Okay, now let's convert that to the number of molecules of EMT. And again, I'm simplifying esomeprazole magnesium trihydrate as EMT. So the number of molecules would be 1 millimole of EMT for every 767.2 milligrams, because that's the molecular weight of the EMT. Okay, and that's why we didn't use 40 milligrams for the amount of the drug in the packet, because that's of pure omeprazole. What I know is the molecular weight of the parent molecule, esomeprazole magnesium trihydrate, the EMT, so that's why I started with the 44.5. So just going back, 30 packets times the weight of the EMT per packet, which was 44.5, then converted to the number of millimoles by dividing that by the formula weight of 767.2 milligrams, and we're finally then in the millimoles of EMT. Okay, now though, the question asked for the millimoles of esomeprazole. So we have to look back at the parent molecule in the molecular formula on top, and remember we said there are actually 2 esomeprazole molecules for every 1 parent molecule of the EMT. So that's why I'm multiplying it by 2 millimoles of esomeprazole over 1 millimole of esomeprazole magnesium trihydrate. When we do that, the EMT millimoles cancel, and our final units would be just millimoles of esomeprazole. So if you do that math from left to right, you would numerically get 3.84, and that would be the number of millimoles of esomeprazole. Okay? And that's the answer to letter A. Moving on to letter B, it says, how many milliequivalents of magnesium are contained in one box containing 30 packets? Okay, so where we've just answered millimoles for esomeprazole, now we want milliequivalents of magnesium. So let's start in the same place, that is, namely the 30 packets. We'll take the 30 packets times the weight of our EMT per packet, which was 44.5 milligrams. We'll convert that to the number of millimoles of EMT by dividing it by the molecular weight of 767.2 milligrams. Milligrams cancel. We're now in millimoles of EMT. Now we need to convert from the parent molecule to the number of millimoles of just the magnesium ion. So I'll remind you, if you look up on the chemical formula above, there is just 1 magnesium in every 1 esomeprazole magnesium trihydrate. So I'm going to put 1 millimole of magnesium on top over 1 millimole of EMT. So millimoles of EMT cancel. I'm now in just millimoles of magnesium. But keep in mind, the question wanted to know milliequivalents. So I have to look at the valence. Since the charge on magnesium is a positive 2, the valence is 2. The valence number would go with the milliequivalents. So we have 2 milliequivalents of magnesium for every 1 millimole of magnesium. So once again, the only units remaining are milliequivalents of magnesium. Do the math left to right, and our numeric value would be 3.48. Just like it was for the number of esomeprazole millimoles, we get 3.48 milliequivalents of magnesium. And lastly, let's answer the last question for letter C. It says each packet is to be mixed with 15 milliliters of water. What is the osmolarity of the suspension, the resulting suspension, in milliosmoles per liter? Okay. Well, when we do these osmolarity questions, we want to figure out the number of osmoles, but we want the quantity per liter. So let's start with 1 liter, which is the same as 1,000 milliliters. Okay, so we'll start with 1,000 milliliters. Let's multiply it by, what we are doing is taking the contents of one packet, that is 44.5 milligrams of esomeprazole magnesium trihydrate, or EMT, and we said to put that into 15 mils. That packet is going to be dispersed or dissolved in 15 milliliters. So we do it that way so that milliliters cancel, and when I multiply the 1,000 times that ratio, I would just then have milligrams of EMT. Convert that to millimoles by multiplying by 1 millimole of EMT over 767.2 milligrams. Milligrams cancel, and I'm back into millimoles of EMT. Now, I'm not worried about valence. I am worried about the number of particles that will occur when I take one EMT molecule and let it dissolve in water or disperse in water. Remember, it's an electrolyte. What will form? In the end, in terms of particles, I will have 1 magnesium particle and 2 esomeprazole particles. Remember, there were 2 esomeprazole molecules for every 1 magnesium. So 1 magnesium plus 1 esomeprazole plus another esomeprazole, 1 plus 1 plus 1, equals a total of 3 particles. Therefore, we put 3 milliosmoles on top for every 1 millimole of EMT. Millimoles cancel, and our final units multiplying from left to right are in milliosmoles. So if you do that math, you'd get 11.6 milliosmoles, and I'll remind you that's the amount specified starting with per liter or per 1,000 milliliters. So 11.6 milliosmoles per liter is essentially the osmolarity, which is 11.6, and that completes this question. All right, let's begin with the next question. And I'll remind you, we have already answered some questions on calcium. Then we've just done one that involved a little bit of magnesium. And so now let's focus on sodium. And the question reads, how many milliliters of a sodium acetate, 16.4%, and this is implied weight per volume solution, would you add to a liter of 0.45% sodium chloride in order to produce a nearly isotonic solution? And I give you the formula there for sodium acetate and its molecular weight of 82, as well as the sodium chloride, NaCl, and its molecular weight of 58.5. Okay? So here's what we're trying to do. So we're starting with a liter of 0.45% sodium chloride. And hopefully by now you realize that's not an isotonic solution. We have talked many times about sodium chloride, that a 0.9% sodium chloride solution is isotonic. So clearly a 0.45% concentration of sodium chloride is hypotonic. All right. So we're going to take that hypotonic solution and try to make it isotonic by adding a different additive, that is namely sodium acetate at a 16.4% concentration, to raise it up to essentially an isotonic concentration. Okay, where do we begin? That's a lot. Well, let's start with the end. What are we trying to make? We're trying to make an isotonic solution. So let's figure out how much sodium, regardless of its source. We don't care where the sodium comes from. If we're making a liter of solution, basically as close to isotonic as possible, how much sodium would it take? So let's just answer that question. Let's start with the volume we want to make isotonic, which is 1 liter or 1,000 milliliters. Let's take that and multiply it by the concentration of sodium chloride we know to be isotonic. All right. So we know 0.9%, which means 0.9 grams of sodium chloride for every 100 mils is isotonic. So if I multiply it by that concentration expressed as 0.9 grams over 100 mils, then milliliters will cancel and I'll have my grams of sodium chloride. But remember, I need to know sodium, how much sodium I need, not so much sodium chloride. So let's take the next step and convert the grams of sodium chloride to milligrams by multiplying by the fact that there's 1,000 milligrams per gram. So grams cancel. Now I'm in milligrams of sodium chloride. I did that so I can convert to the number of molecules or millimoles of sodium chloride. So let's multiply by the fact that there would be 1 millimole of sodium chloride would have 58.5 milligrams, since that is its molecular weight. Milligrams cancel, and I'm now in the number of molecules of sodium chloride. But remember, I'm wanting to count sodium, not sodium chloride. So let's convert to sodium by acknowledging that for every 1 molecule of sodium chloride, there would be 1 sodium. Sodium chloride dissociates to form 1 sodium and 1 chloride. So in this case, I can set up the equation that there is 1 millimole of the sodium ion for every 1 millimole of the parent molecule sodium chloride. So now those units cancel, and I'm now in the millimoles of just the sodium. So let's go ahead and convert that to the number of milliequivalents by multiplying by the valence. So since the valence of sodium is 1, I would have 1 milliequivalent of sodium for every 1 millimole of sodium. I multiply that, and now I can cancel my units, and I'd finally be in units of milliequivalents of sodium. So if you do the math from left to right all the way over, what we have just said, all we've done so far is to say, okay, if I have 1,000 milliliters or 1 liter of solution, to make that isotonic using sodium, I would need 154 milliequivalents of sodium. Okay? That's our overall target. So where do we go next? Well, we know we're going to be using 0.45% sodium chloride as our base solution, so there will be a certain amount of sodium just from the 0.45% sodium chloride. Let's figure out how many milliequivalents of sodium are provided by that base solution. Since we're going to be starting with a liter of that solution, let's start with 1,000 milliliters times its concentration now, which is, we said, 0.45%, which is 0.45 grams of sodium chloride for every 100 milliliters. Now I'm in grams of sodium chloride. Multiply that by 1,000 milligrams per gram. Now I'm in milligrams. I can convert that to molecules of sodium chloride by multiplying by 1 millimole of NaCl, or sodium chloride, has 58.5 milligrams, since that's its formula weight. I'm now in millimoles of sodium chloride. I can convert that to sodium by multiplying by the fact that there's 1 sodium for every 1 molecule of sodium chloride. And then lastly, multiply that, since the valence is 1, there's 1 milliequivalent of sodium per every 1 millimole of sodium. So all the way across, doing the math, I'd have 77, and the final units are going to be milliequivalents of sodium. All right. Can you see that that works very similar to what we did in the beginning, which is what our target, and what we have now found is the number of milliequivalents of sodium that come from just the 0.45% sodium chloride. So since my target is 154, I'm going to subtract from that the amount that is coming from my 0.45%, which we just calculated as 77 milliequivalents. Therefore, what's left over is 77 milliequivalents of sodium. That's the amount of sodium I need from my sodium acetate. Okay, that will be the target I set for the volume of sodium acetate, is the volume I need to provide me 77 milliequivalents. So that's where I'll start. My last calculation is to start with the fact that I still need 77 milliequivalents of sodium. Okay, let's convert that back to the number of molecules. So we'll multiply that by the fact that there's 1 millimole of sodium for every 1 milliequivalent, since the valence is 1. Now I'm in millimoles of sodium. I'm now going to convert that to millimoles of sodium acetate by looking at the formula. And the formula has 1 sodium, Na, for every 1 acetate, C2H3O2. So there's 1 sodium for every 1 sodium acetate. So I'll multiply by the fact that in 1 millimole of sodium acetate on top, there's 1 millimole of sodium. So now I've converted from sodium to sodium acetate. I can now convert to the weight of sodium acetate by multiplying by the fact that there are 82 milligrams of sodium acetate for every 1 millimole of sodium acetate, because 82 is its molecular weight. I'm now in the weight of sodium acetate. Let's convert this to grams before we go any further. So we'll take the milligrams of sodium acetate and convert it to grams by multiplying by 1 gram on top over 1,000 milligrams. That just converts my units to grams. So I'm now in grams of sodium acetate. The last step is to use the concentration of our additive to determine the volume. The concentration we were given in the question was 16.4%, which is a weight per volume, which means 16.4 grams for every 100 milliliters. So what I'm going to multiply is by the concentration expressed as 100 milliliters on top over 16.4 grams on the denominator. That way the units of grams cancel. And if I do that math all the way across, my final units would be milliliters. And if you do that math, you would see that the final volume would be 38.5 milliliters. So to summarize this question, if we take 38.5 milliliters of sodium acetate, we've determined that that would contribute 77 milliequivalents of sodium. By the time you add that with the 77 milliequivalents of sodium already in our liter bag of 0.5% sodium chloride, that would give us a total of 154 milliequivalents of sodium, which we know to be an isotonic solution. And that essentially ends this question. Okay, time for the next question, and we're moving on to potassium phosphate. And I love this question because it goes to show how tricky sometimes the commercial labeling can be. What you can see on the far right is an actual vial label for the commercial product that's defined by the USP. It's a national formulary recipe for potassium phosphates for injection. And it seems so straightforward, but it's not. So let's read this question. It says, potassium phosphates for injection, USP, is a solution intended to provide phosphate ions, or PO4, for the addition to large volume infusion fluids for intravenous use. And so these could include like TPNs. This is a common source of adding phosphate to TPNs, which are total parenteral nutritions, when we're doing IV nutrition for patients. Okay? So it's an additive primarily indicated for the replacement of phosphate. However, it's coupled with potassium, so they both are in the vial. Don't forget, there's both potassium and phosphate. Okay? This is where I think it gets tricky. Each milliliter of the solution consists of essentially two sources of phosphate. That is, part of this injectable, that is 22.4% weight per volume of this solution, contains monobasic potassium phosphate, which has the chemical formula of KH2PO4 and a molecular weight of 136.09, as well as containing 23.6% of dibasic potassium phosphate, which has the formula K2HPO4 and a molecular weight of 174.18. So again, while it's just listed as potassium phosphates for injection, the solution actually has two different forms of phosphate, this monobasic potassium phosphate and dibasic potassium phosphate. And that's what makes using it a lot more complicated than it might seem at first. Okay? Well, let's answer our first question. The first question says, what is the concentration of phosphate in millimoles per milliliter in this solution? Now keep in mind, it's wanting the total concentration of phosphate. It doesn't matter whether the phosphate is coming from the monobasic or the dibasic, but in the end, let's add up all of the phosphate and express its concentration in terms of millimoles per milliliter. Okay? Well, we're going to have to do this step by step. So let's start just with the first one, the monobasic potassium phosphate. Okay? And what we're going to do is start with the fact that we were told we have a 22.4% weight per volume solution. Okay? So from that, we can express that concentration as 22.4 grams per 100 milliliters. So we're going to start off with our concentration expressed in grams per 100 milliliters. All right? Now, we'll leave the 100 milliliters alone until we divide it all out. Let's focus on changing the units, though, from grams of monobasic potassium phosphate to millimolars. Okay, so we'll have to do some unit conversions. The first unit conversion we will do, we'll convert that weight in grams to milligrams by multiplying by 1,000 milligrams per gram. So units of grams cancel, and we're now in milligrams. Now we can convert that to the number of molecules of monobasic potassium phosphate by multiplying by the fact that every 1 millimolar of monobasic potassium phosphate would have a weight of 136.09 milligrams, since that is its molecular weight. Milligrams cancel, and now this is where I'm going to refocus on the structure here. We're now in millimolars of the parent molecule, which is KH2PO4. Okay? But what the question wants is to know how many millimoles of just phosphate, which is the PO4. So if you look at the molecule, there is one phosphate, the PO4 molecule, for every one potassium or KH2PO4. So we're going to multiply this by the fact that for every 1 millimole of PO4, that is contained in 1 millimole of KH2PO4. That way, millimoles of KH2PO4 cancel, and our result would be the number of molecules of PO4. But keep in mind, that's still expressed per 100 milliliters. So we'll divide that out, and our final units would be in millimoles of PO4 per milliliter. So if you do all that math from left to right, you should get a final numeric value of 1.65. And keep in mind that final units would be millimoles of PO4 per milliliter. Now, we can do that same calculation, set up the same exact way, but do it for the dibasic potassium phosphate, which I'll remind you has a different formula. It's K2HPO4. Okay. However, it works very much the same way. However, the starting concentration was different, so we're going to start off with our 23.6% weight per volume and rewrite that as 23.6 grams per 100 milliliters. Convert grams to milligrams by multiplying by 1,000. Convert milligrams to millimoles by dividing by the formula weight of 174.18 milligrams. So now I'm again in millimoles of the parent molecule K2HPO4. We can see by that structure, that formula, that there is, again, only one phosphate in that molecule. So we can multiply by the fact that there's 1 millimole of phosphate for every 1 millimole of the K2HPO4. The millimoles of dibasic potassium phosphate cancel, and our final answer would be in millimoles of phosphate per milliliter. And if we divide it all out or do the math, you should get 1.35 millimoles per milliliter. Okay. Well, the last step is simply to add up. Again, the question doesn't care where the phosphate comes from, so let's take the 1.65 millimolar per mil of phosphate from the monobasic and add it to the 1.35 millimolars per mil from the dibasic. Add those two together, and we get a total of 3 millimoles per milliliter of phosphate. That's the concentration of phosphate in this solution. Okay, part of it is contributed by the monobasic potassium phosphate. Part of it comes from the dibasic potassium phosphate. But in the end, when those are all combined together, the total phosphate concentration is 3 millimoles per mil. And just to double check our work, if you look up above on the vial, you can see right underneath where it says injection, it gives the concentration of phosphorus as 3 millimoles per milliliter, which matches our answer at this point. The next part to this question, letter B, says, how many milliequivalents of potassium are contained in a 50 milliliter vial? So we've gone from calculating concentration of phosphate to calculating the total amount in milliequivalents of potassium. Remember, while it's intended to provide phosphate for IV solutions, we also have to account for the amount of potassium that it includes. So let's calculate the total milliequivalents of potassium in this vial. Well, where do we start? Well, let's start with the volume of the vial, and we have to calculate the amount of potassium separately from the amount coming from the monobasic, from the amount coming from the dibasic. So let's start with the monobasic, and we'll start with the fact that we are looking at a 50 milliliter vial. So we'll take 50 milliliters, multiply it by the concentration of the monobasic, which was 22.4% or 22.4 grams per 100 milliliters. Convert grams to milligrams by multiplying by 1,000. Convert milligrams to millimoles by dividing by the formula weight of 136.09. And we're now in, again, millimoles of the parent molecule, KH2PO4. Now, the point of this is to determine the number of milliequivalents of potassium. So let's convert from the parent molecule to the millimoles of potassium. So again, we can multiply by the fact that there would be 1 millimole of the potassium ion for every 1 millimole of the parent molecule, since the formula is just KH2PO4. There's 1 potassium in every 1 monobasic potassium phosphate. So now we're in just millimoles of potassium. So now we can finally convert to milliequivalents by looking at the valence of potassium, which is 1. Therefore, there would be 1 milliequivalent of potassium for every 1 millimole of potassium. So you do that math all the way across, and your final numeric answer should be 82.3. And the last remaining units would be milliequivalents of potassium. But keep in mind, that's simply the amount of potassium coming from the one source, that is the monobasic potassium phosphate. So next we got to do that same calculation, but determine the amount coming from the dibasic potassium phosphate. Okay, so it's really set up exactly the same. We start with 50 mils times its concentration, though, which is the 23.6% or 23.6 grams per 100 mils. Now we'll convert grams to milligrams by multiplying by 1,000, convert milligrams to millimoles by dividing by the formula weight of 174.18, and then we're in millimoles of the parent molecule K2HPO4, which is the dibasic potassium phosphate. I emphasize that formula because hopefully you realize then what we need to do is multiply by the fact that there are 2 millimoles of potassium for every 1 millimole of the parent molecule K2HPO4. Look at that formula. There are 2 potassium molecules for every 1 molecule of K2HPO4. That's why the conversion is to multiply by 2 millimoles of potassium on top for every 1 millimole of the parent molecule. Now we are in millimoles of potassium. We convert to milliequivalents by multiplying by its valence, which is 1, so 1 milliequivalent of potassium per 1 millimole. And we do the math all the way across, and we get 135.5 milliequivalents of potassium. Therefore, our last step would be to add up all of the potassium, which would be to take the 82.3 milliequivalents of potassium from the monobasic, add it to the 135.5 milliequivalents from the dibasic, and the total amount of potassium in this 50 ml vial would be 217.8 milliequivalents of potassium. Okay, well, let's go back up and look up at the vial again, and we can kind of compare our answer. They list essentially 220 milliequivalents per the 50 mLs. We calculated essentially 218, and we are the one who are being precise here. They kind of rounded their number and cheated there just a little bit. But again, our calculations are correct, and you can see it essentially matches what's listed on the product label. Let's complete the last part to this question. And so letter C, and we couldn't end one of these questions without talking about my favorite subject, osmolarity. So it ends with asking, what is the osmolarity of this solution in the units of milliosmoles per liter, which again are the units of osmolarity. All right. Well, this is going to be very similar. Hopefully you can see the similarity between millimoles and milliequivalents, and finally now milliosmoles. The difference here compared to what we just did for potassium and milliequivalents, where we had to consider the number of milliequivalents, here we're going to count particles. And once again, we have to do it one step at a time. So let's start by counting the particles present due to the monobasic potassium phosphate. Okay. Now, and it wanted us to count the milliosmoles per liter. So let's get our answer, our final answer in the amount per liter. And we'll do that by starting with the 1,000 milliliters. Let's start with 1,000 milliliters, which is 1 liter. Multiply it again by the concentration of the monobasic, which is 22.4% or 22.4 grams per 100 milliliters. Convert that to milligrams by multiplying by 1,000. Convert that to millimoles by dividing by the formula weight of 136.09. At that point, we're now in the number of molecules of KH2PO4. Okay, now we got to count the particles. What's a little bit tricky about this is when it goes into solution and dissociates, you'll have a positive potassium ion come off of the phosphate, but the 2 hydrogens will stay linked to the phosphate. That's why it's called monobasic, is that it stays as H2PO4. Therefore, the resulting molecule has a single negative charge, which is why it only binds a single positive potassium. But the H2PO4 stays together as a single negatively charged anion. Okay, so we have 1 potassium positive plus 1 H2PO4 negative molecule, so 1 potassium plus the 1 monobasic phosphate gives you 2 particles. 1 potassium, 1 H2PO4. That's 2 particles. Therefore, our final step is to multiply by the fact that we would have 2 milliosmoles, since there are 2 particles, for every 1 millimole of the parent molecule, KH2PO4. Do that math across, and you'd get a total number of 3,292 milliosmoles. Keep in mind, that's the number of milliosmoles in 1 liter. All right, let's do the same exact thing for the for the dibasic potassium phosphate, but you'll see something kind of cool, different here in a minute. But it all starts the same. 1,000 milliliters, since we're calculating the amount per liter. 1,000 milliliters times its concentration of 23.6 grams per 100 mils. Convert grams to milligrams by multiplying by 1,000. Convert milligrams to millimoles by dividing by the formula weight of 174.18. So now we're in millimoles of the dibasic, which has the formula K2HPO4. When that goes into solution, what dissociates is you would have two potassium ions, positively charged ions, but you'd have two potassiums to bind with the one dibasic phosphate molecule, which is HPO4 negative 2. HPO4 has a negative 2, which is why it binds two positive potassium ions. So if you think about the number of particles, you'd have a potassium plus a HPO4 minus 2, or a dibasic phosphate. Therefore, you get 3 particles out of one molecule of the dibasic potassium phosphate. So that's why we end this calculation by multiplying by 3 milliosmoles per every 1 millimole of the dibasic potassium phosphate. Okay, you do that math all the way across, and you get 4,065 milliosmoles. And again, that was per the 1 liter we started with. So to finish this question, we just need to add up all of the total osmolarity. So let's start by taking the 3292 milliosmoles per liter from the monobasic potassium phosphate. Add to it the 4,065 milliosmoles per liter from the dibasic potassium phosphate. And the total osmolarity for this solution is 7,357 milliosmoles per liter. And if you got all of that, then you got the right answer. And you might have wondered, oh my gosh, did I really get the right answer? Because that seems like a really high number. If you remember when we talked before about kind of isoosmotic forces as it relates to blood and plasma and lacrimal fluid and biologic tissue, it's really about 280 to 300 milliosmoles. Okay, this is way high. This is 7,000 versus like 300. Well, look up above for the vial. What does it say in red? It says for IV use only after dilution. This is absolutely not intended to just be injected into a person because it is super hyperosmotic, hypertonic. So this would create all sorts of havoc if you just injected it. Remember, this intent was to use a small amount of it, the amount that you need to dose to give somebody the right amount of phosphate, and to put it into like a 2,000 or 3,000 milliliter TPN bag that provides somebody their entire fluid and calories for the day. So this solution is only ever intended to be highly diluted and only small amounts used to be able to provide right amounts of phosphate in much larger bags. All right, well, you have reached the last question. So if you're still with me, we're on our last question, and this is one of my earth-friendly questions because it's recycled, meaning that you've actually seen this question a little bit before in our moles and molarity review in Chapter 9. It was our last question there, but we didn't ask the same question. So we're going to take that same setup and kind of apply your new set of knowledge and see if we can go a little bit further. So the problem says, a medication cassette is prepared using 8 grams of carbenicillin disodium, which has the brand name of Geopen. Anyways, the 8 grams of carbenicillin disodium is diluted to a total volume of 250 milliliters using 0.45% sodium chloride. Now, this ambulatory pump is actually set to deliver this 2-gram dose over an hour. Okay, so the volume of fluid is that it actually gets infused is the volume it takes to give 2 grams of this drug, and then it stops. And it doesn't do anything for another 6 hours. 6 hours later, it gives enough fluid again to give 2 grams dose. So it's not running continuously. It infuses 2 grams and then stops, but repeats that dose every 6 hours. And lastly, I give you that the molecular weight for the carbenicillin disodium is 422.36, and I'll remind you for the sodium chloride it's 58.5. Okay? Now, kind of an initial question to set up before we answer the more important questions is simply this. How many particles and what is the valence for both the sodium chloride and the carbenicillin disodium molecules? Because again, if we're going to calculate osmolarity or osmolality, we need to know particles. If we're going to calculate milliequivalents, we need to know valence. That's kind of why I like this last question for this section. Those are the two main terms we've covered in Chapter 12 to make sure we can handle both milliequivalents as well as milliosmoles. All right. So to answer that question, let's start with the simple one with sodium chloride. I even have little pictures I got off the internet. So you'll notice sodium chloride, it starts as a solid, but when you put it into water, it dissolves, and we're going to assume complete dissociation. It dissociates into two particles, one sodium molecule with a positive valence and one chloride ion with a negative valence. And again, the valence actually is 1. Okay, so it's a positive 1 on sodium and a negative 1 on chloride. So if we just look at this, we can conclude that for sodium chloride, it has a valence of 1, okay, and it would produce 2 particles. All right? Now, the carbenicillin disodium is where it gets a little more confusing if you're not careful. So let's look at this model carefully, this molecular structure that came straight out of the package insert and listen to the word, carbenicillin disodium. So you'll notice there's this kind of complicated molecule here in the middle. But if you look on the far left, you can see a sodium, an Na with a plus, next to an oxygen with a negative 1 value. But on the other side of the molecule, you can see another oxygen with a relative negative next to a sodium with a positive 1 valence. So what you can see, why do they call it carbenicillin disodium? Because essentially the carbenicillin has a negative 2 charge, and so it's offset by having 2 sodiums. Okay, so it takes 2 sodiums to interact with one carbenicillin molecule because the valence of the carbenicillin molecule is negative 2. Okay, therefore, we can conclude that the valence for the carbenicillin is going to be 2. And the number of particles, though, is going to be 3, because here we make the molecule by combining it with sodium, and it takes 2 sodiums to equivalent 2 positive sodium molecules to equal 1 negative 2 carbenicillin molecule. So sodium plus carbenicillin equals 3 particles. Now, with that information in mind, we can try to actually apply it to answer some questions. First question here now really is, how many milliequivalents of sodium will the patient receive per day from this infusion? Okay. Well, it's complicated because they're getting sodium from the carbenicillin and they're getting sodium from the sodium chloride solution that the carbenicillin is dissolved in. So we're going to have to calculate the amount of sodium separately. So let's start with the carbenicillin. All right. Let's start with the fact that this patient is getting 4 doses per day. Okay, they're getting a dose every 6 hours. So 24 hours divided by 6 is 4. 4 doses per day. That's what I start with on the far left. Let's multiply that by the fact that we were told that each dose has 2 grams. So we'll have 2 grams on top per dose. That way the units of dose cancel, and we're in grams per day essentially. Now we can convert grams to milligrams by multiplying by 1,000 milligrams per gram. We're in units of milligram. Let's convert that now to the number of millimoles, or the number of molecules of carbenicillin, by dividing by its molecular weight, which was 422.36 milligrams. Milligrams cancel. I'm in the number of molecules of carbenicillin. Okay. Now this is where you got to think back to that chemical structure. We said that in solution, carbenicillin disodium would produce 2 sodium ions for every 1 carbenicillin molecule. So that's why we're going to multiply this by the fact that you get 2 millimoles of sodium for every 1 millimole of the parent molecule, carbenicillin disodium. That lets us convert now. Now we're in the units of just millimoles of sodium, and we can calculate the milliequivalents by multiplying by the fact that the valence on sodium is 1. Therefore, there's 1 milliequivalent of sodium for every 1 millimole of sodium, and millimoles cancel, and our final units are in milliequivalents of sodium. Do the math from left to right, and we see that in one day, having 4 doses of this carbenicillin will provide us 37.9 milliequivalents of sodium. And I'll remind you, that's just the sodium from the carbenicillin. So our next step is to determine the amount of sodium from the sodium chloride solution, the 0.45% that we have. Okay? Let's start in the same place. It gets a little tricky in the beginning, and it ends up being the same. So the start is the same, 4 doses per day. Okay? We also know that each dose was 2 grams of carbenicillin. So we're still going to multiply 4 doses times 2 grams over each dose, so that doses cancel. I'm now still in the same place. I'm in grams of carbenicillin. This is what's unique about the sodium chloride. We need to convert from the weight of carbenicillin to the volume of solution that will provide. And what we knew is that the overall concentration of this cassette had 8 grams of carbenicillin in a total volume of 250 mils. That's what's important. Because I'm now going to multiply by that concentration expressed as there in a total of 250 milliliters, there was 8 grams of carbenicillin. Now grams of carbenicillin cancel, and I would have a volume of this solution to provide that total amount of drug. Now I can convert that volume of the overall solution to just the volume, or the weight that solution would have of sodium chloride. Because I know that volume is 0.45% sodium chloride. I know that that's a weight per volume concentration, which would translate as 0.45 grams of sodium chloride per 100 milliliters of solution. This way, milliliters of solution cancel, and now I'm finally in grams of sodium chloride. All I have to do is convert that to milligrams by multiplying by 1,000 milligrams per gram. Then I can convert that to the number of molecules of sodium chloride by multiplying by 1 millimole over its molecular weight of 58.5 milligrams of sodium chloride. Milligrams cancel. I'm now in millimoles of sodium chloride. I want millimoles of just sodium, and since there's 1 sodium ion for every 1 sodium chloride molecule, I multiply by 1 millimole of sodium over 1 millimole of the sodium chloride. And then lastly, convert that to milliequivalents. Since the valence of sodium is 1, there would be times 1 milliequivalent of sodium for every 1 millimole of sodium. Doing the math left to right, my final answer would be 19.2, and my units milliequivalents of sodium. So it's 19.2 milliequivalents of sodium that come from the volume of my 0.45% sodium chloride solution that this patient would be infused in that same 24-hour period. So to end this question, all we need to do is add up the amount of sodium from the carbenicillin, which we said was 37.9 milliequivalents. Add to that the amount we get from the 0.45% sodium chloride, which we said was 19.2 milliequivalents. So 37.9 plus 19.2 gives us a total of 57.1 milliequivalents of sodium. And that's the amount of sodium this person would be getting per day from both the equivalent from the carbenicillin as well as from the solution. So 57.1 is the answer to this part of the question. But we're not done. Oh no, there's one more to kind of answer here. It asks, what is the osmolarity of the solution in milliosmoles per liter? Okay, and osmolarity is the milliosmoles in a liter. So again, where do we start? We need to count particles. And again, we're going to have to count particles of carbenicillin, and we're going to have to count particles of sodium. There's just no way around it, of actually sodium chloride. So all of our ingredients, we need to count the total number of particles. So let's just start with the carbenicillin. Okay, so carbenicillin, again, we want to know the milliosmoles per liter. So let's start with a liter of this solution. So we start with 1,000 milliliters. Multiply it by its concentration, which was 8 grams of carbenicillin for every 250 milliliters, so milliliters cancel. Convert the grams to milligrams by multiplying by 1,000 milligrams per gram. Grams cancel, we're now in milligrams. Let's convert that to the number of molecules of carbenicillin by multiplying by 1 millimole of carbenicillin would be 422.36 milligrams, which is its formula weight. Milligrams cancel, I'm in millimoles. Now, remember, I don't care about valence. I'm not worried about milliequivalents. I'm counting particles. So now we got to go back to that structure of carbenicillin. When we stick 1 carbenicillin molecule into solution, keep in mind, it's carbenicillin disodium. So what we get is 1 carbenicillin plus 1 sodium plus 1 sodium. So there are 2 sodiums and 1 carbenicillin, meaning there are 3 particles. Therefore, that's why we multiply this times 3 milliosmoles for every 1 millimole of the carbenicillin disodium. Therefore, when we do the math from left to right, we'd get a final value of 227.3, and that would be in milliosmoles. And I'll just remind you, though, that was the number of milliosmoles per liter of that solution. Okay, let's find out how much we get from the sodium chloride. All right, so let's start at the same place. We have 1,000 milliliters since we want to know the amount per liter. So we'll times that times its concentration, which was 0.45% or 0.45 grams of sodium chloride per 100 mils. Mils cancel. To convert grams to milligrams, multiply by 1,000. And then to convert to millimoles, I'll multiply by 1 millimole over its formula weight of 58.5 milligrams. Now I'm in millimoles of sodium chloride. What happens when you put sodium chloride in solution? It dissociates and you get 1 sodium and 1 chloride. So for every 1 parent molecule, you get a sodium and a chloride. That's 2. So there would be 2 particles or 2 milliosmoles for every 1 millimole of sodium chloride. So now when you do the math from left to right, your final answer would be 153.8, and the units are finally milliosmoles, and that was the amount per liter. So as a reminder, to find the total osmolarity, you would take the contribution from the carbenicillin, which we calculated to be 227.3 milliosmoles per liter. Add to it the osmolarity produced by the sodium chloride, which was 153.8. Add those two together, and you get 381.1 milliosmoles per liter, which is essentially the osmolarity of the final solution. So, to conclude, this was the last question. Hopefully you found this lecture helpful as well as a good review over everything that we've covered in this chapter 12, which again is to be able to convert from milligrams to millimoles, then from millimoles to either milliequivalents using the valence or to milliosmoles by counting the number of particles. So again, I hope this was a helpful review.